In this video, we're going to see Hall effect and its application. Hall effect is a very important phenomenon used in electronics. It is named after Edwin Hall, who discovered it in the year 1879. Before getting into the basic physics behind the Hall effect, let me speak out the basic statement of Hall effect. The statement is, when a current carrying conductor is placed in a transverse magnetic field, say B, an electric field E is induced in the direction perpendicular to both current I and magnetic field B. Let me write down the statement for reference here. To prove this statement and understand the basic physics behind this, let us consider a piece of material with dimensions, say length L, width W and thickness T, and let us assume a current is flowing in this direction, say I. And to have reference directions, let us define some directions. Let's say this direction is X and this direction is Y, and this direction, which will be coming out of the video towards you, is Z direction. Three of them are mutually orthogonal to each other. It means perpendicular to each other. Now let us consider magnetic field B in Z direction. So let me mark it down here. Let us take magnetic field in Z direction, okay, and this I, the current, is flowing in X direction here, right? Magnetic field in Y direction and current in X direction. Now let us consider this material is, say, n-type material in which majority carriers are electrons. So let us consider an electron, okay. The electron flow will be in the opposite direction to that of the conventional current direction. So if you consider an electron here, its direction will be in this direction which it will be moving in, okay. Let us consider this electron whose charge is minus Q, where Q here is 1.6 times 10 power minus 19 coulombs, and it is traveling in minus X direction with a velocity, say, V. Let me write down V in minus X direction. Now you have a magnetic field in Z direction, electron moving in minus X direction with a velocity V. Now there will be Lorentz force applied on the electron here. Let us consider Lorentz force equation. F equals to force applied on the particle, in this case the charge is minus Q, times the velocity minus X, okay, vector quantity, cross product with the magnetic field direction here, which is Z. Now what this Lorentz force equation means is, if a particle of charge, say minus Q in this case, is moving with a velocity V in a magnetic field B, then this F will be the force that will be acting upon this charged particle, okay. Taking this into consideration, now this is moving in minus X direction and magnetic field is in Z direction, so the force will be in minus Y direction. Let us see here, this is in minus X direction, okay, velocity, and magnetic field in Z direction. If you take cross product, minus X direction cross product to Z direction, you'll have Y direction, right? This will be Y direction. Now you have a negative sign here coming from the charge of the electron, so the overall force will be acting in negative Y direction. So this electron will be pushed towards the bottom face of this material. Now for reference, let me write down or take this face as phase 1 and the top one as phase 2, okay. So now this electron is pushed towards the bottom face of this piece of semiconductor. Now the electrons will be pushed towards this side and electrons start accumulating, okay. As the electrons start accumulating, what happens is this phase 1, will be negative with respect to the phase 2. So we can take the potentials with respect to each other. The top phase will be positive and the bottom phase will be negative. So we have a potential difference building up as the accumulation increases. Now if we observe here carefully, as the electron accumulation is increasing, the potential difference is increasing. As the potential difference is increasing, the electric field will be increasing as well. Let me take a different color. Let's take orange. Okay. The electric field will be in this direction. Okay. Which is in minus y direction because of this potential buildup. Now if we observe carefully, this electric field is in minus y direction. Okay, now electric field will apply some force on these electrons. Okay, the force applied on the electrons will be equal to minus q, the charge of the electron, times the electric field here, which is in minus y direction. If you see, this direction is minus y, and the charge, if you see, the overall will be in y direction. So the force is in y direction. If you look at this Lorentz force equation, it is in minus y. So now let's take a step back and see, as this Lorentz force equation is making the charged electrons accumulate at bottom face, the potential difference increases. As a result, electric field increases, and electric field will put some force on these electrons in the opposite direction. So at some point, these force due to Lorentz force and force due to the built-up of electric field will balance out each other. Okay, let's call this electric field as Hall electric field EH. Okay, so at that point where these forces both equal each other, there won't be any further accumulation of electrons at the bottom face. Okay, that's a steady state. Now if we see this, phase 1 and phase 2, the charges accumulate at phase 1 and stay there, and there is a potential difference which we call VH. And relationship between EH and VH is EH equals VH over the thickness of the semiconductor material here, and the forces are equal here, and I'm going to take the magnitude of both, and if we write Q times V times B, now I'm not taking any directions and just taking the magnitudes. And if you see here, V bar cross B bar, we are writing VB because as we are assuming V and B are perpendicular to each other, so V times B times sine theta will be equal to V cross B. So sine 90 is 1. So we'll have V times B, which is equal to Q times Hall electric field EH, which can be written, okay, again like Q times VB equals Q times VH over T, and let's cancel out Q. So we'll have V times B equals VH times, okay, this is over T, VH over T. So this is an equation. Now if we see J, the current density, equals to the current density flowing here. Okay, I is the current flowing into it, and we can say J is the current density flowing into it. So J equals Q times N times V velocity of the charges here. So if we rewrite this particular equation here, we can write it as J over Q times N times B equals VH over T. Let me rewrite this J in terms of I. Okay, I over W times T. W times T is the cross section area. Okay, J equals I over W times T. If you rewrite it here in this equation, we'll have I times B times W times T times Q times N equals to VH over T. Let's cancel out this thickness which is common here and there. Okay, and let's take some space down. Okay, if you rewrite this equation, we'll have I times B over W times Q times N equals to VH. Okay, now 1 over Qn is equal to VH times W over B times I. This 1 over Q times N, we are going to call this as RH. Okay, RH is Hall coefficient. So if you rewrite this equation, let me rewrite. RH equals VHW by B times I. This is the equation for calculating Hall coefficient. Now if you look at it carefully, VH is something which you can calculate by using a measuring device for voltage across these two phases, phase 1 and phase 2, and width we can know from the dimensions of the material you're going to use, and current is the value of current flowing into the material, okay, and B is the magnetic field in which we place the semiconductor material, or say conductor. So we can calculate this RH. Now we have another quantity, let's say J. We have written it so far in Q times N times V, right? We can write it also in sigma times E bar, and this Qn can also be written as Qn. Drift velocity V can be written in terms of mu times mu n actually times E. Okay, this electric field here we are pointing out is not EH, it is a different electric field. It is corresponding to the voltage you apply across this semiconductor material across the length, due to which there is electric field E and due to which there is current I. Okay, this is a different electric field. So if you rewrite this, okay, we have sigma equals to Q times N times mu n. If we rewrite this, we know that RH equals 1 over Qn. So if we take this, sigma equals 1 over RH times mu n. Okay, and let me rewrite this. Mu n equals sigma times RH. This is another important equation. Okay, so now we have two important equations. One is RH, which is Hall coefficient, equals to VHW by BI, and the other is mobility, which can be measured by knowing the conductivity and RH. Okay, so far we have considered n-type material, in which, let me summarize the formulas we derived. RH equals VHW over B times I, and mu n equals sigma times RH. The sigma is here sigma n, right? So the electrons were accumulating in the phase 1, which is the bottom phase. Now let us consider if it is a p-type, what will happen. Let me take a hole here, okay, which is traveling in this direction, right? When you have current flowing in this direction, hole will be moving in this direction. Let me take it with velocity v. Now if you take Lorentz force equation, F equals, the charge here is positive Q, which is electron charge, but it is positive here as it is hole, Q times V cross B, right? If you take the vector quantities, V is in, let me take the directions here again, Y, and this is Z. It is in positive X direction and B is in positive Z direction. If you take that properly, X times Z, you will have this V cross B pointing in minus Y direction, and overall will also be minus Y direction. So F will be in Y. Now these holes will be forced downwards, so these holes go and accumulate in the phase 1, okay, or the bottom phase of the semiconductor material here. Okay, so now as the holes are accumulating in the bottom phase, this becomes positive with respect to the top phase. So there will be a Hall voltage built up, due to which there will be electric field. This electric field will be pointing topwards, which will actually oppose this Lorentz force. As a result, these forces will balance out at some point where it reaches steady state. So if you do the same derivation for the p-type also, okay, you'll have the equations RH equals to VHW over B times I, okay, where in this case, the previous case, okay, in n-type, RH was equal to 1 over Q times N, whereas in this case RH equals to 1 over q times p, where p is number of holes per centimeter cube, and here n is number of electrons per centimeter cube. If I write mu p, mobility of holes, sigma p times RH. Okay, so if you're given two materials, okay, one is n type and the other is p type, so if you apply current in x direction and magnetic field in z direction, if you see top face positive and bottom face negative, it is n type. If you see top face negative and bottom face positive, it is p type semiconductor material. Okay, let us see a few applications in this case. Okay, the first one is measuring carrier concentration. How do you measure carrier concentration? So we have seen we have RH, right? In both cases we have seen, which is equals to VHW over BI. As all these are measurable quantities, because you are applying the current through the semiconductor material and you are keeping that semiconductor material in a magnetic field B, which should be known, and VH is the developed one, which we can measure by using a voltmeter, and width W is the dimension, one of the dimensions of the semiconductor material. So RH we can obtain, which for n type RH equals to 1 over q times n. We know the charge of the electron, so n we can find out. In case of p type, we'll have 1 over q times p. We can find out p. So we can find out carrier concentration. And finding out mobility, right? Mu equals sigma RH. So now as we can find out RH and sigma in both cases, n type and p type, we can find mu. Either it may be mu n or mu p. So we have seen mu n equals to sigma n times RH and mu p equals to sigma p times RH. And magnetic field meter, how do we use this concept for measuring magnetic field? As we know, RH equals VHW over BI. If we write VH, we can write it as RH times I over W as a factor times B. Okay, if we take this as a proportionality constant, keeping I as constant or a known value, so VH will be directly proportional to B. The voltage which you measure across the two faces will be directly proportional to the magnetic field in which you keep the semiconductor material with known current flowing through it. Okay, now how do we use this as Hall effect multiplier? Okay, if you see this carefully here, RH, okay, if we rewrite the equation again from here to here, VH can be written as RH over W times B times I. So we get a Hall voltage measurement which will be directly proportional to the multiplication of two parameters, okay, a magnetic field and current flowing through the semiconductor material, right? Okay, so these are few of the applications, and practically you can see some applications like building sensors with this Hall effect concept, and you can see some computer peripherals like keyboards which are very reliable, okay, which are built with Hall effect. Okay, and there are multiple applications based on this concept, Hall effect. And thanks for watching the video, and if you like the video, please do subscribe, and thanks for watching.